Hello everyone. We've been talking about the principle of superposition, and we've already used that to take two identical travelling waves, crash them into each other, and we've seen that the result of that is a standing wave. However, it's probably a little bit more natural to wonder what happens if we take two waves that are actually travelling in the same direction. What happens when they superpose over each other? So to investigate this, let's take a wave source. The wave source I'm going to be choosing today is a speaker. But of course, you could use this to apply to any kind of wave you like. And in fact, we'll definitely be talking about light waves using this principle later on. But you could take water waves or electrical signals or whatever, and we'll get the same result. So our speaker is going to be producing a pressure wave, a sound wave, which will look something like this. It's traveling towards the right. You can see as the speaker cone, which I haven't animated, pushes in and out, it displaces the air, which is the medium, to the left and the right. And we go up and down. If I put my ear in the path of this wave, I should be able to hear it. And what I hear will depend on the wave itself, which, as we recall, has an equation that looks something like this. So the displacement of our medium, or our pressure in this case, has an amplitude, A. It's got a wavelength, which is related to the wave number, K. It's got a frequency, which is related to the angular frequency, omega. And it's also got this phase constant, which tells us basically where our wave is starting, what our wave looks like at time t equals 0 and position x equals 0. You can also condense all of these little bits and bobs from the argument down and call that whole argument of the sine function there just the phase, which we've given the symbol phi here. So let's take a second identical wave. I say identical, but it's going to be coming from a speaker that's in a slightly different position. So it looks something like this. So these two speakers are placed some distance apart. Of note, the two speakers are producing exactly the same wave, just in different positions. You can tell this because when the displacement from the right-hand one is up, the displacement of the left-hand one is also up, and vice versa. So it's natural to ask ourselves first, what are the equations of these two waves? We've got two waves, we can't call them exactly the same thing. So we'll call the first one D1, the displacement produced by the first speaker, D1, and we're going to just replace everything that's relevant with different ones. So because these two speakers have different x positions, we can consider shifting the speaker to the left or the right as being like a coordinate transform. So we're just going to label the x axis of speaker 1, x1, and of course they could each have a different phase constant depending on where they're starting. As they're actually identical in this case, they'll have the same phase constant, but we'll investigate that in a little bit. And of course we can just smush all that together and just call it the phase of speaker 1. Speaker 2 has something similar. So we've done the same thing, we've just relabeled x to x2, and we've relabeled phi 0 to phi 2 naught, because it's not really a nice way to put two subscripts on the same value. Okay, so what am I going to hear? If I put my ear down here, what will I hear? Well, to find that, we're just going to add the two together. Say, principle of superposition says the total wave is going to be D1 plus D2. So it'll look something like this. So you can see here, well, as far as the equation goes, D1 plus D2 seems simple enough. This is a bit of a mess. It's a bit hard to pass that. But you can see graphically, and really we're just going to be looking at these mostly qualitatively. We don't really care exactly what the waveform is. But things to note, it has the same frequency as each of these two waves does. So I'm going to hear the same frequency. But the amplitude in this particular case is bigger. Because they're not quite in phase, it's a bit, it's not big, it's not small, it's just it's a little bit louder than it would be with just one speaker. There are two main situations we're going to be concerning ourselves with when talking about interference in one dimension. So if we shift our speaker a little bit to the left, we'll see that now both the speakers are producing sound waves in phase, and because they're now exactly one wavelength apart, with the wave produced by speaker 2 perfectly overlaps the wave produced by speaker 1. And the end result, if we add these two together, will naturally be double what one of them would be. So you can see here, we call this constructive interference, and the amplitude of our resulting wave is double the amplitude of our original wave. The other case which we're going to be interested in is if we take our speaker 2 and we push it a little bit further to the right. So instead of being one wavelength away from speaker 1, it's now 1.5 wavelengths. And you can see, because we're 1.5 wavelengths, even though the two speakers themselves are producing exactly the same peaks and troughs at the same time, because they're a wavelength and a half out, whenever one of these red waves is at a trough, the green is at a peak. So if we add these two together, what will we see? Well, whenever there's a peak from one, there's a trough from the other, so they're going to cancel each other out perfectly. And so we call this perfect destructive interference. And the amplitude of our resulting wave is going to be 0. Now, what I haven't talked about yet is what happens if we actually change the phase constant of either of these waves. So let's just go back for a moment and consider two speakers which are perfectly aligned with, which are perfectly one wavelength away from each other. If we now change the output of speaker 2 so it's not quite in phase, so here, when speaker 1 has a peak, speaker 2 is somewhere in the middle, and we add these two together and we see the end result is something a little bit, it's not perfectly destructive, well, it's hardly destructive at all, it's actually a bit bigger, but it's not perfectly constructive either. We don't get that double our amplitude that we'd like. The other thing we could consider is if we change the phase constant of speaker 2 so that it's producing something which is out of phase with speaker 1, we get something that looks like this. Now you can see whenever speaker 1 has a peak, speaker 2 has a trough. We add these together and we get 0 amplitude. Exactly the same as if we were, say, 1.5 wavelengths or any number and a half of wavelengths away from each other. This is actually the principle if you have noise-cancelling headphones. This is the principle they run on. The idea is the headphones will produce a wave which is just perfectly out of phase with the incoming wave, and they add together to cancel each other out. So to wrap all this up, if we have two waves traveling the same direction at the same wavelength, they're in the same medium, so they're traveling at the same speed, we'll get perfect constructive interference if the difference in phase between the two waves is an integer multiple of 2 pi. So that corresponds to an entire cycle. And we'll get perfect destructive interference if they're an integer plus a half multiple of 2 pi. So I guess 1 pi, 3 pi, 5 pi, so on. In general, you could get this phase difference by some combination of shifting the position and shifting the phase constant. But most of the time, we're going to just be considering the effect of shifting the position, changing the length that each of those two waves has to travel, and we'll just generally we'll consider the source of the waves to be the same. So we're going to apply this kind of principle to more complicated situations in the near future. We're talking about interference between light rays reflected from the top and bottom of a piece of glass or oil. And we'll also consider interference in 2 dimensions. So if we have our sources placed somewhere in 2 dimensions and we're placed somewhere else, how these 2 different waves will interfere with each other when they hit our ear. So I look forward to that.